Yeah, we've got it. I've got it. All right, let me just make sure it's all working. Come on. I think I got it. Yep. Okay, we're good. Let's do that. No. I just need to just face it somewhere other than looking at me. It's weird.
Oh, okay. Oh, because it's also we are in the
streams it live.
Okay.
You can't have it. When we did it the first time, I tried to do it with just the audio but no video. But no video means no audio, so we lost the first half hour of class.
Okay.
It has to have video.
Oh, okay.
Yeah.
So you need to face.
So just facing the wall.
Okay. Okay. So first of all, we all went to this Steve Lawrence class. What is your thinking about it? But be frank, don't. I will not tell David.
So I think it was like generally pretty interesting in terms of his different experiences with like the industry and how big data is affecting all these different parts of the world. I don't really know if he quite gets like for me, like some of the privacy and some of the...
He seemed to be more excited than critical.
Yeah.
But...
And I don't know if that came from like a technical perspective or a...
Okay, let's put that way. I will help you because obviously it was a great visit for me in many respects, but can tell you frankly, I was quite unimpressed by the talk.
Mm-hmm.
So that's the thing, and in a sense, and this is what relates to, in a sense, to this class. In my opinion, is that again there is. I heard. So did you have rephrasing my question? Did you walk out of that seminar with the feeling that you learned something that you didn't know, or that you
no, not particularly. It was like big data is a thing. There's this approach in business that people are using data to find insights. They don't necessarily care about causation so long as there's sufficient correlation, and they'll use it for whatever means. And sometimes it screws up, and that's the story.
Yeah. So in my sense, that the guy is missing. First of all, I think he's using a kind of old perspective. And it was just telling stories that we all knew one way or another, and that's why, in that sense, I was a kind of unimpressed. I was expecting more vision, more foreseeing the future. I don't know, something that was story that I didn't. I could not imagine, or and especially, for instance, for the privacy part, is underplaying everything in a sense. It's okay. It's we will figure it out in a sense. Was the but for me, what was missing, and this actually misses, is a miss in many of the recent books on big data, etc. Is the fact that everybody just look at these business analytic components. So they miss completely what we are doing in this class, the modeling part. And the fact that at a certain point, what is really worrying and scaring me is that, probably with the data that they have, you know, our little models and our little investigation will be just a pale imitation of what they can do at Facebook, at Google, at the big companies. Sure. And when you start to see that our pale imitation, because we work with limited data, whatever, you start to have predictive power on on major social phenomena, on population unrest, things like that. You understand that actually, they might really have a knowledge, develop a science, etc. That it's within their closed and inner garden, and that is much more, even more, in a sense. For me, it's more. I'm positive, but it generates anxiety in the sense that it's much more than just the privacy of a single individual.
There's an entire sort of
it's the privacy on the future. It's the fact that you access information that other people cannot access.
Mm-hmm.
The fact that you might do a prediction even of 3 hours in advance of something concerning a social movement. Is a foresee that we don't have just because we don't have those data. And that's not just because of the simple analytical correlation that you can develop, but also because you can develop models and you have microscopic models, etc., that they know. It's not that they don't, that they are not interested in. So that's the other thing. And for me, all that part is completely missing. So there is no perception of it in that analysis, and for me it was a little bit how to say, lacking of some more exciting, because it's also the exciting part for me, but as well it's what really opens the doors to the future more than just looking at what was the past, the 10 years in the past years in the area. But in a sense, how it relates to our class is that what we are doing is exactly to go one step further. So we are interested in not just in the correlation, but we are interested in the causation. When you build models which are microscopic, which contains information on single individuals or are mechanistic, you are trying to define rules and dynamical rules that you can directly associate for causation as a causation principles and not just as a statistical correlation. So that's in that sense that talk was related to our class. It's what you can say is that it was not there. So our class is not there, but this is what you have to keep in mind. Okay, so can I see a little bit of what you did with the model?
Sir?
Yeah.
Sure. Did you really? I mean,
did you really?
No. Did you really expect though for you to take something away from that talk? Like maybe I would, but he's a journalist. Like
not technically.
Yeah.
And it happened to me in certain talks of to come out with a vision that I didn't have, with a thinking that I didn't have, or I could not read on the pages of almost every blog. That's the thing. So this is for me, getting to an author like him that has so much experience, has wrote so many times about big data, etc. I would have expected, to have that kind of thinking that perhaps we as technical people from time to time don't have, just because we are not, we are too much focused. We are in fighting our own battle one by one, and from time to time you get, just in this fog of war, and a person like him, I would have expected a vision from very high, telling me, okay, look, this is what has been so far, this is where we could go in 10 years or in 5 years, these are the threats as well as the excitement that I see. And I think he has that in mind. It was just the talk at the end was, was all focused on this rear view that is in the book, but I think it's talking about 10 years ago more than what is happening now. Okay.
Yeah, okay.
So you want to see something?
Yeah.
So first, the result of the image that you get. There you go. So this would be, the blue line would obviously be susceptible, green would be recovered, and orange would be infected.
Okay, how many are in total?
There was 1,000 as requested. The initial infected count is 10. The initial recovered count is 0.
Okay, so
And then
this is, what are the equations that you're using?
right here.
Yeah.
So let's see here. It's been more than a week since, or no, like about a week that I wrote this ago. So a little rusty on what it exactly reads as. But, so you got mu beta, number initial, and the initial infected goes into the function. That's all that you need. And this thing is basically just storing the counts. And every t-step, another one of these is generated based on the previous one. And they are appended into this, which allows you to visualize it afterwards. So you just set the initial one, and then every single step, you feed the previous step into it with mu and beta. And that's sufficient to generate the new current status. And then you just keep on looping over this whole section until the infected is 0, because once there's 0 infected, the virus can't spread anymore.
Yeah, but then you are fooling me. Come on.
Okay. We're going.
Because
So,
this is the code that
yes.
you did with Nicola.
No, this is the code I wrote for this.
Sure, because this is stochastic. There is a random less than mu.
There's a what?
So this part, you are making
Yes.
random extraction here.
Yes.
Why you are making random extraction?
Because you have a...
I told you we were just solving a deterministic equation.
Oh, okay. So what you need to do is just every time remove exactly
what I told you is that, and this was the past time, what I shown to you was the integration of we wrote down on the whiteboard, now I will do it again on the classboard, the equations for the deterministic iteration of the model. And what I wanted to see is the deterministic part, because this one, it enters a completely different thing, because this is also, this you are trying to do random extraction of each of individual to see if they recover. And then you see that actually you are doing something else, that is current status divided the population size, current status, you are using now the beta as the probability of transition, but then you are using also this one, you multiply by the current status divided by the population size. And so it's a little strange as well, because this is, what are you doing is to compare the random number with beta, but I don't understand what is the effect of the mass action, basically.
Let's see here.
Because the probability of transition for each individual. Wait here, don't move.
I also did a random. He didn't make that explicit. Well, maybe he did.
The probability of transition for each individual, P from S to I, is equal to beta I over N. Okay? So now here I don't understand what you do, because you take the current status of the susceptible, you multiply by the current status divided the population. So you do this. But then I don't know why you compare just with the random extraction with the beta. So it's not clear to me. This is correct for the recovery, because if I is in the current status, but this you are multiplying by that, and it's not.
Let's see what I had in my notes.
It's not correct. You know Python, no?
Yes.
So you can read that stuff.
Why did I have it as STIT over N? Did you have it as STIT over N?
Yeah.
My understanding was that the new...
Yeah, but then it's not stochastic. Okay, if you use these, and this is what you have to completely understand. One thing is if you solve the stochastic equations, and then you include noise, random extraction. Another thing is if I'm doing a deterministic equation where I'm taking the average, but here you are not taking an average. You're doing a random extraction.
Okay.
So, now let's go back to the equation.
You're looking for a little star?
Eh?
What are you looking for?
I'm looking for that. Let's do like that. You two go on the other side. No, because otherwise it's really... I was tempted to write here, but if I do that, then it's
you run the risk
$10,000 damage to the place.
You can write on the outside of this?
We can write on the outside, but not on the inside. Okay. So what we did the past time, what we had was the following. We say, I want to know what is the ST at time t plus 1, ST plus 1, I, the number of infected at time t plus 1, and the number of recovered at time t plus 1, if I know, and this is what, the things, the IT, ST, RT, okay, so the previous time step.
Yes.
And what we wrote are iterative equations that relate the average value. Do you remember? Because we said, okay, what is ST plus 1? ST plus 1 is made by two contributions. Obviously, you have the susceptible that were at time t. And then what we did is also to minus the number of susceptible that goes into
infected
the things. And we wrote these as delta, let's write delta S minus, okay? So these are the one that goes out. I t plus 1 is equal to I t. Then there is a minus
for I to R.
Delta I, a plus delta I plus, that is means the
incoming
people that are incoming. And then we have another term that is the one that goes out. So minus delta I minus, so the one that goes out, okay? And then we have those which are to RT, and then plus the one delta R plus. Now, the thing is that we need to find who are those, we try to find what are those elements, okay? And what we did as an exercise with you was to find the expression for those quantities, but we find expression for the average quantities because we said, okay, now what we know is that each individual who is, this is the minus, who is an infectious individual can go as a recovered with a probability which is equal to mu, okay? And this probability is equal to the inverse of the average time the individual is in the infectious state. We say that, no? And so if we have that, what we get is that delta I minus, so the one that goes out of the infectious compartment, is equal on average to this probability times the number of individuals which are in that class at time t.
Mm-hmm.
Okay? And so this is the first piece of information. Then we have a second piece of information, that is the probability, and actually I should use a different colors. That is the probability that a susceptible goes into an infectious individual. And this is what we have wrote there, or I already, yeah, it's almost invisible. And we say that this is equal to beta IT divided n. And so here we made a very clear statement about the assumptions we are doing. So we are forgetting any contact, anything, etc. And we are saying, okay, each individual that is susceptible has a probability of being in contact with an infectious individual, which is equal to the fraction of infectious individual in the population. So if I have one individual over 1 million, my probability will be 10 to the minus 6. I have one individual over 2, my probability will be 0.5. Okay? This is called the mass action law. The mass action law is just basically establishing a proportionality between the people who are infected and the force of infection that this susceptible individual feels. Then there is a prefactor beta, which is not even a probability. And that's why you have to be careful when you write that thing, beta. Because beta actually is a rate, is a probability per unit contacts, and actually also the number and multiplies by the number of contacts that you have. Okay, so it's a number that in principle could be larger than 1, because it's a probability per contact times the number of contacts. And then, since you have this small probability, that means that only very few of your contacts generally are infected, this becomes a probability. Okay? So this is, and this is a probability per unit time. So this is the one that is defined as a probability. The rest is, this is a variable that you cannot use just as a simple probability alone. Is this one the probability? When you have this probability, you can write the same thing that we were writing here, because the delta S minus are equal to what? Are equal to the number of susceptible times this probability P S I. And this is equal to ST IT divided N times beta. But this again is not a probability. This is an average number. Okay? Now I can write the equations at this point, because at this point I can say ST plus 1. I will get crazy with these markers. We need to get the, I don't know, I will tell Nancy to buy, I don't know, there will be expensive markers that works.
Well, I'm saying, probably the case is like the back is,
Sorry?
like the color.
The color of
like
the back
white.
doesn't
The
really.
color of the back is bad, yeah, so it's, well, you know, but we are with the little star, and, you know, it's really not, okay, we need to find, let's go pinkish, my daughter would love it. Okay, ST plus 1 is equal to ST minus this stuff, which is equal to that. So is plus ST IT over N times beta. Now, what I have that is good is that I know that what goes out of S is what comes in the IT plus 1. So what I know is that these two terms are equal. And so I can write I t plus 1 is equal to it. I'm sorry, this is not a plus, this is a minus, guys. Please follow the things. Tell me, Alex, what the heck are you doing? Because otherwise, it plus, now this is people that enters this compartment, beta it st divided n. Now I have to evaluate what goes out of it, and what goes out of it is this one.
Mm-hmm.
So it's minus mu it, and then I have a third equation, rt plus 1, which is equal to rt
plus mu
plus mu it. So this is the system. But now you see that what I wrote are equations for an average quantity.
Mm-hmm.
So these are average quantities. What I'm writing is a recursive equation for the average number of things that I see in the system. I can start with an S0, I0, R0, which is equal to something that is an integer or whatever, but I could also use numbers which are an average. I would say that on average my initial condition is that. So these are equations that, as you see, they are not completely true. So we have made assumptions. This is the simplest things we can do, because we can calculate quickly those quantities. Okay? Mm-hmm. Those equations, and this is what I told you the past time, if you solve those equations with the same initial condition 1,000 times, every time you will get exactly the same result.
Mm-hmm.
So why I got alarmed as soon as I've seen your plot?
Because they'll be different.
Because your plot is
little,
noisy,
yes.
And if you rerun the things, it will be a little different. So there is something that doesn't work in this formalism, okay? The only things that in your computer can change from solution to solution is little difference due to the fact that your code will always round out numbers. And so you might have little differences depending on the precision that you use. If you use a double precision, things that you get this that is 10 to the minus 8, before you see any difference. But, so everything should be the same.
Mm-hmm.
This equation is deterministic, is an average value. It is called continuum deterministic version of the SIR model. Continuous because those quantities, since are averages, are not integers. It's not really 1, 2, or 900 individuals, but could be 2.5, 2.6, etc. So it's an average quantity. So you are assuming that you are doing this you are running the simulation, the real simulation, the stochastic simulation many times, and then this is what you would get on average. Actually, we will see, probably not today, but the next time, that this is not even true. This average equation is not the average of the stochastic, of the solution, of the stochastic solution. This is for discrete time step. So I'm using a time that is discrete.
Mm-hmm.
We will see that this is, again, can be formalized in a way. Once you have this, you can write this in a simple form that is the differential equation format. But actually, it's just making the time continuous. It's not adding anything to this representation. It's still an equation that relates average quantities. This kind of equation, as I told you, is very, very good generally when you have a large number of individuals in all classes. These are the classic equations that you use in chemistry, in physics, because you have the Avogadro number of particles. The density of particles is so high that those equations, the average, reaction, because that would be molecules, this would be atoms that react together and change, or molecules that change. Those average quantities, it works very, very well, because of, that the larger is the sample and the better is the average, because the theorem of the law of the large numbers, no? So
Yeah.
if you have a quantities, the larger it is, the mean, becomes a convergence with a noise that becomes smaller and smaller, the larger is the sample. So
Sure.
in an infinite time limit, in an infinite size limit, in principle, your mean is exactly what you will observe. There is no error.
Unless your distribution does not follow the central limit theorem.
Unless the distribution doesn't follow. Yeah, but this we are talking about Poissonian or binomial processes, so everything is well behaved, okay? So what I do now, let me do something very simple. I rewrite those equations in a way that is this one. St plus 1 minus St is equal to beta St it divided n, okay? And then I take I t plus 1 minus it is equal to beta St it divided n minus mu it. And then finally Rt plus 1 minus Rt is equal to plus mu it. Now what I can do is these things. I divide both sides by delta t. This delta t is the 1, but I write them making this delta t arbitrary. And I divide all that side by delta t. I have to divide those sides too by delta t, and I will do that by transforming this coefficient in a rate. This probability now, this number becomes a rate. So per unit things. And this is something that is and then what I do is that I can take the limit for delta t that goes to 0 of this side and this side. And this is what transforms in the differential equation. This is the symbol is delta t of St is equal to beta, but now is a tilde because it's a rate, is another quantity, is another quantity, is another number. So I t s t divided n, the t I t equal beta. This is minus, beta tilde I t s t divided n minus mu I t, and simply the t r t is equal plus mu I t. This symbol of differential equation, it tells me that I'm now looking at infinitesimal time step, so I have continuous variable also in time. And this is the format that this is a tilde 2. This equation we can solve. There are a lot of analytical ways to solve those equations, to manipulate those equations in a way that is a little bit more convenient than the discrete form. Keep in mind that, although you will see in all books that the name of parameters is always the same in both versions of the equations, you are talking about different quantities. In one case is a rate, in another case is a probability. Okay, and those are different things. For instance, those numbers might be much larger than 1 when you have differential equations. Because it's not a probability, it's a rate. It's a probability per infinitesimal unit time. So it's totally different. Since delta t goes to 0, that number could explode. When you are in this version that is the discrete, those things should always be well-defined numbers of probability. Now, again, if you solve this equation, you might know that there are ways to solve differential equations. There are codes that are called integrates numerically differential equations. The computer, what it does is to go back to this and take this limit very, very small. But then there are a lot of tricks in doing that so that you do this limit very, 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 very small in the integration, okay? And so there are the Newton methods and many, many others that you can use, okay? Generally in Python, you should find a routine where you plug just the equation and then it integrates the equation. So you don't even to tell anything, you just decide what kind of approach you use for the solution of the differential equation. You give the equation and it gives you spit out the result. Again, this is another equation that is deterministic. Okay, so there is no noise in here, no probability, no fluctuations. If I do the simulation, it will be always the same. Now, the difference between a stochastic model and a deterministic model must be something that you have to dominate because it's totally different. We will see the theory coming from this process is different from this theory. You will see that there are different effects and things that if you use this approach in a stochastic system, you will never see those effects, okay? So, that's the reason why I want you really to focus on that. You know, this one thing is to do the probabilistic version. Another one is the deterministic one. Is that
so? These two cases has different outcomes.
Yeah. So no, okay. This one, and this one are both deterministic.
Okay.
And so you will get the same results. Well, the same results.
In the limit, right?
Because
discrete.
One is discrete, and therefore, if you don't have a delta t that is small enough, you will see differences. If you do the differential equation, you will have a smooth things that interpolates. But you know, basically, it's the same equation. Okay. What we are not tackling at all here is the stochastic part, okay? And so this is what I want to show you today, the stochastic part, how to do the stochastic part. Now, before I do that, what did you do with this?
So I did the same thing he did.
Okay, and that's, guys.
And I just was trying to see if I could, on the fly, make the discrete version. And I wrote it up, but yeah.
I think here, I want to imagine there is good faith, that you took the code that you use with Nicola, and then you arrange in a way to use that. No. So why you went this way then? I told you it's deterministic, so you don't have random extraction. A code that is, really...
I just didn't write deterministic down in my notes, which was my fault.
Okay.
Yeah, so my notes just
the equation
are all
that
the
we wrote
equations.
were deterministic, and the point was actually to see those equations. How is the behavior? Funnily enough, when you will do that, you will have a very similar profile of what you have seen. You will see the susceptible that goes down, the infectious that has a peak, and the remove that goes up. Yeah. But you will see that everything is very, very smooth and always the same. Yep. Okay, so.
Yeah, no, I mean,
okay, so
I don't
you
even,
are in the same.
I don't even know you looked at Nicola's. I didn't remember what we.
Yeah, I didn't look at Nicola's.
Yeah, because I thought we were doing something different.
Indeed, it's different. But then if you do the random version, then you have to do it the correct one. So you have really to consider the probability, and then what you can do is to try for each individual what is the probability of transition.
Yeah.
Now, again, we're doing the SIR model. This would be for any model with individuals and with whatever the probability is telling me. It doesn't have to be an infection, a contagion. It could be a transition because you listen to news. It could be a transition because you interact with somebody. It could be not a disease, but your smoking habits. Is your probability of being arrested if you are a smuggler. So there are models about that. So it's not that, and we will do those exercises. I will tell you now we model this, okay, and you will write equations that simulate that. Now, however, let's keep using this example as the SIR as the basic gym for us. Now we have these two probabilities which are relevant. P of I to R, which is equal to mu. And then P of S to I, which is equal to beta I over N. Those are the two probabilities. So now what I have in a probabilistic vision, conceptualization of the model, is that I have boxes. Inside those boxes, this is the box for S, this is the box for I, and this is the box for R. And what I have is that I have a lot of susceptible here. I have the infectious here. And I will have some removed here. Okay? So this will be my system at time t. And now I want to do what happens at time t plus 1 in a stochastic way. So what I have to do to make this happen? It's really that, the system. Now we are working with 3, 7, 1, 2, 3, 4, 5, 6, 7, 8 particles in each box. So these are, this is the total number of individuals I have. What I should do now, what the computer should do.
So for S to I, it has to go through each one of those cases, each one of the 8, and with a mu, or with a beta probability, choose them?
Not a beta probability. Again, the probability is the... I will make this carpet a disgusting mess, all pink. This is the probability.
Yeah, the beta I.
Okay.
Oh, beta I, yes,
yeah.
Of course.
So what you have to do, first of all, is to count how many I you have, and what is your population. Okay. Then
and that's modeling the probability of
yeah.
actually interacting with one of these people
yeah.
times the probability of transmitting the disease.
You will get a number here.
Yes.
This number is called force of infection, and is the probability that in the discrete model you will use, okay? Okay, so now what you do, you take each one of these particles, and for each of these particles you toss a coin. You do what you were doing in a sense. So you get a number between 0 and 1, compare with PS to I, and if it's smaller than the number, you move the particle from one box to the other, otherwise it stays in the other box.
Yep.
The same you do here, but it's a little bit more simple. You just have mu. So for all infectious individuals, you flip a coin. If that coin is a positive event, you will
Then you move them over.
you will move the things there.
Yep.
Probabilistically, what is that process? For each particle, what I'm doing?
When you're moving them from.
What is this? This is a random, uncorrelated extraction, no?
Mm-hmm.
Brownian motion.
With a certain probability that is the same for all the cases. There is a little more convenient way to write this. Instead of going through all the particles. Now think in terms of computational thinking. What you have to do here is to extract a random number that is equal to the number of particles you have in each box. Now, if you are simulating a population of 1 million people, every time you have to do 1 million random extraction to toss coins and see if
You have to do it a
work
million
or not.
times.
Okay.
Sure.
There is a smarter way to do that. This is when you have this, it's like if you have ST event, you consider success, although it's not a success to be infected, the fact that they transition from one to another. So you are in the event occurring with that probability. And this is a bunch of events, ST trials, they are called trials, with probability P S I.
Mm-hmm.
If you have these two elements, you know that the number of success is distributed according to the binomial distribution. Okay? So you know what is the probability to have one event, 0 positive event, 1 positive event.
So you just choose choose randomly out of the distribution instead.
And you choose one number that is this binomial outcome. You have a routine in Python, binomial of ST PSI. The Python will return a number that is according to the probability distribution of the binomial. It's one extraction, even if you have 1 million of particles. Okay? The same you do here. Now the trials is the number of particles IT, and the probability is mu. And then, you know, basically you have that those trials, you have a binomial extraction IT mu, and a binomial extraction ST, and here you can, instead of using that, you can use beta I over n. Those two numbers are your random version of the plus and minus that were entering in the compartments. And so you have the extraction, and now it's you are doing a stochastic model. Okay? This stochastic model is called chain binomial process, because this is binomial extraction, and then you create a chain in time that relates what is at time t with what is at time t plus 1. The full stochastic description becomes that st plus 1 is equal to st, and now what you have is minus the binomial of st beta is over n, and then you have it plus 1, which is equal to it plus the binomial of st beta is over n minus the binomial of it mu, and then rt1 is equal to rt plus the binomial of I and mu. Okay, this equation is the set of stochastic equation. And this is called chain binomial process because you see is a chain, is a Markov chain, the extraction are independent of one from each other, of binomial processes. What is the advantage? What you are doing with this stochastic process is that you have just two extractions instead of thousands or millions of random extractions. So your code is n, where n is the number of particles, times faster than if you do the how to say the simple particle approach.
Mm-hmm.
Now my question is, what is that? Is an equation? Is that an equation? You guys.
So it's the same as what we did over here. We just take the average of.
But that is not an equation.
Well, it's a probabilistic.
Because
system.
this is not anymore. This is a formal. This is a. Is not anymore analytic that you can solve. You see that this one is a probabilistic kernel, so it's not anymore a real equation. You cannot just do a solution. Each history now will be different. So this is not, this is an equation for one history of the system. Every time will be different. It's not actually an analytic equation like the other one. So this you plug in the computer, you do once, you repeat the second time with the same initial condition, and it will be different. Okay? Because every time that will return you different numbers. The different numbers get recorded in the history, and then you will get different
So this is the stochastic version of
of
the deterministic equation. Okay.
Now, this equation would be a simple stochastic equation if I would have only kernel like that. This is a fixed probability.
But it's more complicated because of the I factor.
Because of this.
Yes.
What is that? This is the non-linearity of the system is there. Why is non-linear? Because let's imagine that what is the non-linearity here?
Well, as I increases, you're collecting more and more of T.
Yeah. You have a kind of feedback. Let's imagine that you are very unlucky in the first. Let's imagine we start with I equal 2 in the system. We initialize the model. Well, let's imagine also that n is of the order of 10 to the 3. Your probability, I'm sorry.
The S shouldn't be there.
This is bad.
Yeah, the S.
The S is not there, only the probability, okay? I'm very sorry. So the S is not there, it's just the I. You see that this probability is very small, it's tiny, it's 2 over 10 to the 3.
But as I increases...
So you might be generally not reasonably unlucky to get that the binomial will return you 0. No one of the process will give you an infection number.
Mhm.
And then instead, this mu is always the same, is 1/3, for instance, 1.5, depending on the number of days per particle is there. And so, those two guys could simply recover,
Because
and
if
the
it's one,
epidemic is done,
if it's 1/3, we expect within
Yeah,
3
basically
days it's going to be
after
done.
Yeah, so, there is something balance. What happens is that, however, you have a probability that this binomial will return 50 infected particles. The probability will be small, but it's there. The point is that at the next time step, you will have I, which is 50 plus the previous one. And so this number is very large. So this probability change according to what was, the history of the system in terms of the infection that have been generated stochastically. And so what happens is that here the system is totally nonlinear. So you can get an acceleration. If you are unlucky at the very early step, the system will accelerate. It will be more and more, the force of infection will be larger and larger. While instead, if you are unlucky at the very beginning, the system will probably not take off. So you see that you can have very different history and very different outcomes from the same process. Mm-hmm. In general, indeed, if you want to have something that is well behaved in the computer, you have to set initial conditions which are reasonable. Reasonable means that you need to have at least 10 to 20 people already infected, so that your probability that you don't just shoot to 0 right away, it's not relevant, it's not very large. And plus there is another condition that is where that we will see in the next classes, that is what we call the epidemic threshold, and actually this is the concept of phase transitions and basically macroscopic change of the system that will determine if those equations have a solution with the number of infected individuals that is relevant or not. That will be very important, however, because that's our understanding of the system. This is when we have a model, we have not yet understood anything about the system. So we have written a mathematical description. Now, what we have done in the class of the past day and the class of today is to have two mathematical descriptions. One is deterministic and another one that is stochastic. Okay? Those descriptions, in principle, we hope that are not too far, okay? If they are too far, it means that we have a problem. So the model, depending on what we do...
Too far in terms of modeling reality?
Yeah.
Is that what you're saying?
Well, also, before we go to the reality, let's do too far in terms of the solution. Mm-hmm. So let's imagine I solve this system. When I solve these systems, I have one solution. 3 cures, which is one solution, is deterministic, is always the same. If I do those equations, every time I will have a different story. However, I can do an average over all those different stories. If the average that I get from here is very far from the average that I get there, well, I'm doing something that is not correct. If the two things are reasonable, and what is reasonable we left to you as an exercise, then it means that the system is you are providing two different descriptions of the system which are consistent. Then we have to compare with the reality, and that's a different story. Mm-hmm. There is one more thing. The hope that we have, and initially most of the people has, if goes through the regular book approach, is that these kind of equations are really the average of those equations. This is what you would like to have. So, okay, this would be the full deterministic thing, the full stochastic things. But if I imagine that I do 1 million realization, I take the average, I get exactly what I get from this equation. Mm-hmm. And one of the questions that we want to answer in this class, we will answer this question if this is true or not. Most of the people think this is true. Your guess is, I already more or less told you it's not true, but you have to guess, you have to find why it's not true and how much is not true. Okay, so this is one thing that we can summarize in a little more structured way. Where is the VG? Can I do the VG? You see, I'm old. If I do like him, 6 miles on the bicycle and then I'm here, then I'm dead. Simply that, really. So let me try to do a recap of the things so that we try to fix what we are doing, because the whiteboard is good, but then this is I will share to you the webpage with those notes and the other notes that you need. We say that this transition S plus I, when I say S plus I goes into 2I, you see that I'm really doing what in chemistry is called stoichiometric relation. So I take two molecules or two atoms and they generate some other aggregation of molecules or atoms, okay, according to a certain rate. Now, the rate that I define, or the probability, is the transmission rate per effective number of contacts per unit time, the beta, plus the proportion of contacts that are infectious in the population, I over n. Okay, this is my way to model the process of infection. We call those kind of interaction the two-body interaction, because the process of infection depends on the fact that you hang around, have contacts, or are in a place where somebody else has been there, where you are in contact with him, etc. So you need to have two bodies, okay? This is different from the recovery process that is a one-body process. It just depends on your system. As I told you, this is a complete general scheme. It's not, keep in mind that is very general for modeling everything, okay? It's not just for infection. And also consider that this kind of mass action is what we generally do in most of the models as the first approach. We consider that certain probability of transition, whatever they are given as an average of over the system of a certain quantity. For who is a physicist, or had an experience in physics, or probably remember from Laszlo's Barabagic class, this is called also mean field approximation. Why mean field? Because you imagine to be in a place where there is a field describing the level of infection that is totally flat, okay, is the average. In epidemiology, this is really instead an epidemiological term, is called random mixing. Random mixing assume that those particles here and those particles there are in a sandbox. Yeah. You are just shaking them and everybody is impossibly in contact with everybody. So what you do is that you consider this random mixing, you count the number of infectious individuals, that defines a force of infection on each of the particle individuals. Now, we are doing a class for a PhD in network science. You should immediately tell me, this is not true. You are lying. You are a liar. You are, a crook. Yeah, because actually the structure of the system will be this one. This guy will be in contact with these other two guys because they are in the same office or is the same households. So what you have is that at the end, you see, this is the same system. In this modeling, conceptual modeling and because here we are not, you see that we can do, and this is again the difference between the conceptual representation of the system and the mathematical representation that we produce. We are still, when we do the random mixing, defining this particle shaken in a box. This is still our way of conceptualize the system. The same conceptualization goes into two different mathematical modeling forms, but there is the same concept and the same assumption behind. You, as a network scientist, have to tell me, no, this is the network. And so you see, in this case, with the random mixing, mean field, whatever, each particle feels the same force of infection. In a network, those two particles have force of infection 0. This particle too has force of infection 0. This poor guy has not force of infection 0 and probably has a much larger force of infection. So you see that what I'm doing, and this is why it is called homogeneous assumption, mean field, random mixing, I'm washing out all the differences and putting an average quantity on top of each individual, while instead this is not the case. So this is the first thing that you have to keep in mind, because in this class what we will have to do is to say, well, we need to work on this. Now, how we will describe that? There is a way that we can model this or not?
Yeah.
No.
What? Depending on depending on the network, you can model it on a network,
on
but
the on the knowledge of the network, many things. So now, yes, of course, yeah. Otherwise, we are done. Next week we are done, and then you are free. No, so we will have, but that's, you see immediately that both conceptually and both mathematically is going to be a much harder work. Actually, mathematically we can do little in a sense, and then we are saved by the computational approach. Otherwise, it would be not easy. This is the probability we were defining. Okay, this is given those two quantity. I want to evaluate this quantity. So that's. Don't tell me I just want to repeat things until you know by heart, because this is in the next this week and the next week, this is the basis of everything that we will do. We want to have those extractions. So we say that the number of trials is ST, and this is the probability of success of the trial, the probability of getting infectious. Here you see that I'm keeping a delta t that will fly around, because I'm assuming that this is per unit, is a probability per unit time, and so I'm trying to, but actually delta t is generally equal to 1, so we don't explicitly consider in the equation. But since here I'm writing equation that is delta t instead of t plus 1, I need to keep this that give me an idea that is a probability per that unit time delta t. So it's a quantity that refers to a specific delta t. And you can imagine, if I tell you what is your probability of becoming infected in 1 day or in 1 hour, that will be totally different, okay? The number of contacts that you have in 1 hour or in 1 day is different. I could even consider 1 week for other diseases. And so it's that changes. This is the equation that I write stochastically. So the new number of susceptible individuals is a function of the number of susceptible individuals and then a binomial extraction. And this is the binomial distribution. This is another distribution that you should sculpt in your, right lobe or whatever, because this is crucial. All discrete individual process is this distribution, especially if you have small numbers. If you have big numbers, what it does become? Okay, so if you have 1,000 individuals and then a small probability, and then you imagine that probability is going to 0 and the number of individuals of trials is going to infinite, it becomes a Poissonian distribution. Both of them are, somehow are in the family of the Gaussian processes. So they are defined by well-defined tails. There is a mean, there is an average, etc., etc. Okay? And this is the expression, this is the probability that you have K success out of N trials with probability P. This, is there are various...
I'm sorry, Alex.
Yeah.
If it goes to a Poissonian, P has to be really, really small, but that's in general, like our case, like the number of infected people is really, really small at the beginning.
Yeah. You get a Poissonian if your force of infection, so you have you assume that a process becomes Poissonian for two reasons. One, you have a large population, and then your force of infection within the population is small. If you have a large force of infection in the population, is not Gaussian. Is a Gaussian. Because a good approximation of this is the Gaussian distribution. So, in Python, you should have that. So you should have a routine that right away, when you have those two numbers, N and P, the trials and the probability, you get, a K which is drawn according to this distribution. This distribution obviously changes according to the number of trials. So this is the equation for the IT plus delta T. So the only thing that I'm adding now is this binomial that gives me the recover transitions. And then I have an equation for RT plus delta T, and it's just that one. Now, another thing that you can tell me is, Alex, you are so redundant and boring. Because this is a system with n fixed number of individuals. So by definition, this third equation is not needed. You have the conservation of mass, the conservation of individuals. So you always have that RT will be equal to n minus S minus I. So you don't need a third equation, okay? So when you have integrated two equations, that's more than enough. And this is the SIR model in its full entirety and in the stochastic version. This formulation is a very good formulation if you speak computer, okay? If you speak programming, because that's easy, you can do. If you speak analytics, if you want to do any analytic calculation, you look at this one and say, oh, it's a big problem, okay? It's not that you cannot do things. There are a lot of mathematical approaches to work with stochastic processes, but they are very, very, very tough. And that's why all the modeling is generally first built with those differential equations and the average values, because we can do pencil and paper. And before the computer era, it was possible to do work. Now this one is wonderful, and I think there is a lot of beauty in it, because it's a much more realistic representation of the system, but it's useful just because we can plug into a computer code.
What are like some examples of analytical approaches to this?
Oh, we will go through.
Okay.
To a few of them. Okay, yeah. There are, one is that one approach that has been, again, worked a lot in the past is that you transform the differential equation in a stochastic differential equation. So you add the noise term, which is follow those distribution is related to, etc. And then there are a couple of approaches to stochastic differential equation, Stratonovich, whatever, and then you do results. Another is to work with Markov chains and discrete processes, and you can get results for average value, convergence, and things like that. It's highly non-intuitive in my way. So you need to be a good mathematician. So you enter a different world in a sense. The other limitation of those approaches that might be very important because they can give you a rigorous foundation to certain results. But the other limit of those approaches is that as soon as you complicate this structure,
It's really hard.
it's way too much. Okay. So the equations we work, for instance, every day, they have at least 7 or 8 compartments. There are, all things. If you start to get that, it's not even a binomial at that point. In some cases, you have multinomial processes. We will see what they are, but basically, it's a definition of the binomial process in which you have a number of trials, and then you have more probability of events. So you have a vector of possible outcomes, okay? And so that, and those outcomes are statistically non-independent. So this is the simple things that you get if you forget about everything. So this would be the 3 equations. You see that we have got into something that is so simple that a kid can work with it. The only thing is that delta S and delta R now are those binomial extractions. And now random numbers. Now random numbers, you are expert. With Nicola's, in Nicola's class, you should have seen random numbers, no? No, a little bit. Yeah, so you know that random number need a seed, generate a function, so it's a crazy number that you type, monkey style on the keyboards, and that's is the initiator of the random number generator. You need to change that seed if you want to get different results, because if the seed is the same, the sequence will always be the same. This is the way we work on the computer with the random events. You know that the random number generator is not a problem for small things like we get a small population of 1 million individuals. 2 is a small things in general, whatever. As soon as you have many millions of random extractions, the random generator is a serious business. Don't use cheap random generator, built-in random generator, etc., because those random each random generator has a certain validity. After a certain length of the sequence, you start to get correlation, to get patterns of various kinds. These are the kind you don't want in a random number generator. So you don't want repetitions or sequences which are repeated. This is not. You want to have an expected distribution. So if you want something that is between 0 and 1, you need really to have something that is between 0 and 1 and not always on a specific limit. You want a complete lack of predictability. So if you have always a 4 after a 5, there are those subtle things, and so there is an art of working with random number generator. You find that in numerical recipes, and so there are general things. But please watch out if you do at a certain point. If in your job you will do things which are numerically, challenging with a lot of random number extraction or a lot of use of random numbers, watch out what is the code you're using. This is the pseudocode. The pseudocode is what I should see in your Python code. Mm-hmm. Or in your R code or whatever. But the pseudocode is what you should do. Set the disease parameter value, set the initial condition, set the time step by making your life very easy, delta t is equal to 1, always. Define the variables, auxiliary variables, set of variables at the beginning, loop on time as you were doing till you don't have any more infectious individual, and do the various pieces. So the increments are the binomial extraction calculated. You use the auxiliary variables to update the variables. You map these into the next time step variables, and you repeat these at will. So start to think in pseudocode. Okay, so this is very, very useful. Allow us to talk without going into the details of the you put the commas or not in the right place, the semicolon, etc., etc. And also, perhaps somebody wants to work in a different language. So this is the way to talk in terms of modeling. So what you have done here is the actual definition of the model in a computational language. And now those equations have a meaning. All those equations here in a pseudocode have a meaning, because they are actual extraction, etc., etc. This is, for instance, what you could do. You have 1,000 individuals, 10 of them, however, are infectious, no recover yet. This is how the system starts. You calculate the first two probability. One is the one of recover, and the second one is the one of infection. Mm-hmm. This is given by those expressions. So you see that I to R is always 0.2. It doesn't change. It's always the recovery probability. You see instead that the S to I changes according to the number of infectious individuals you have, because you have the mass action law. You see, this is the first event, is that you have 5 infection and 3 recovery. 3 infection, 2 recovery, 2 recovery, 2 infection, etc., etc. And then you have the evolution of the system. This would be the stochastic version of the system. You see that it's noisy. It's exactly what you were doing, although I think your equation were not correct, because you were extracting on a random number beta, and not with respect to the probability I over n times beta.
Yes.
This fluctuation is because, for instance, at a certain point you might recover more individuals than what you generate, and so your number of infectious individuals goes down, etc., etc. You will never see those in the deterministic equations. Indeed, what you can do is to generate the second set, a second realization of the same system with the same initial condition, but now you have another stochastic realization. So you use another random seed generator for the random number. And obviously you see you will have different results. The extraction is different, so the number of infection generated is 3 and the number of recovery is 2, and so on and so forth. This is all different. Then the number will be different because the probability of infection becomes updated in a different way by the number of infectious individuals. And so you see that at the same time, step 5, the two systems are in two different conditions. Mm-hmm. And if you look at the curves, you will have that the same epidemic as one realization, a stochastic realization that is this one, and another stochastic realization that is this one. So this is very different. And here is where you have to start to ask yourself about the reality. What we have in reality, when we measure an epidemic or any other phenomena, is one instance of the process. That instance could be any one of those. Actually, since in principle there are an infinite number of possible instances, you cannot say, okay, if I see this in reality, right away I can map and I can say something about the process. I need to have a statistical analysis that is based on the many realizations I can generate. And here I want to have the 15 seconds of capturing the beauty of the computational approach. Because the computational approach is the way we can look at all the possible instances of reality. This has never been possible. This is the magic of what the computer does. Allow us to look at whatever could happen out there. You are really looking at all possible solutions and then trying in this huge catalog of stories to look the one that best resemble the one in the real world. But keeping into account that you, through the computer, can access the entire world of opportunity, of possibilities. Indeed, if we do the same process with those two parameters, beta 0.4, mu equals 0.2, and all the things we said, this is what you get if you do 20 or 30 realizations. And you see that, luckily enough, otherwise we would be something that is totally useless. The reality has many faces, but they are not completely inconsistent. So there is a consistency. And this is where at a certain point we will need to do the statistical work. Okay, how we decide if these parameters are good for the real world outside. How I decide if this model is good with respect to what I see outside. That is still a problem that is far from us, okay? Mm-hmm. That we are just looking at the model. What we have in the model is aware that there is an uncertainty. And the uncertainty is crucial because it's the inherent stochastic fluctuations of the system. This is a complication, but is the plus, okay? This is where you become powerful, guys, in the modeling, because you can look at those fluctuations. Never trust any model that doesn't have stochastic fluctuations. That's now I can say after many, many years. And now we do the first things that relates to what we were doing in the past class. So we take all those curves and we do a simple thing. We take the mean of all the values. And then we get a curve that generally is much better. Is this black curve that is the mean of the distribution. So you see that we start to construct a statistical world in which we say our model produces a typical behavior, and then I have variation around that typical behavior that will be my confidence interval. Mm-hmm. And I need to be able to quantify a confidence interval, and then ask myself question on how to map reality into this typical realization plus the confidence interval. We will go through that, not now. Okay, summary. Guess what you have to do the next time?
Make that chart.
Huh?
Make that chart.
Exactly. I want this from you.
Good.
Okay, so binomial realization, many stochastic realization, and then I want the average. For real. Okay, do a clean work, try to work with that, use those parameters so that you know that this works.
Instead of 3 and 5 is 0.3 and 0.5 that we used last week.
And we will take it from there. I think this is good for you too if you can do the Python code with it, okay? You are exempted from Perhaps you will do the class about the MCMC.
Oh yeah, I will do the class.
I don't know. We'll see. We'll talk.
Okay.
Cool.
Yeah, I mean, like what I did, like when I was taking the MCMC, they were doing like determining stochastic, like solving the stochastic.
Yeah.
And their model is so complicated for
your little thing.
If like we want to implement like minor population, this.
No, it's impossible.
It's goddamn
Margaret, those kind of equations are the basic equation, for instance, we use in LIM and we use in most of the models. You know, it's because basically the binomial chain processes is what we use to keep the discrete nature of the system, so that we don't have problem with small numbers, etc., etc. So all the equations that we have in our approaches are like this one. Also, when we do agent-based model, we will see that much later. What we do is that we transform those models in a big network, and then we do random processes on the big network.
In terms of random seeding and did you? So you said be very careful of that. I've done a lot of agent-based modeling in general and just seeding, but I haven't paid a ton of attention